In the vast expanse of digital communication, Chapter 3 delves deep into the intricate dance of TCP and UDP protocols. How does data traverse networks with unwavering certainty, and when does it dare to embrace the thrill of unreliability? Picture this: TCP, the meticulous guardian of data integrity, ensures every bit finds its destination without fail. Contrast this with UDP, the daring maverick that values speed over guarantees, embracing a more carefree approach to delivery. Together, these protocols shape the backbone of our interconnected world, balancing reliability and efficiency. As we unravel the mysteries of TCP/UDP, we uncover the essence of network communication, a delicate interplay of order and spontaneity. So, join us on this journey as we navigate the realms of certainty and chance in the digital realm. Welcome to our journey through essential networking concepts. Today, we dive into the intricate world of network protocols, starting with the TCP handshake. This vital process governs how connections are born and bid farewell between devices. Moving on, we'll explore congestion control, a key player in managing network traffic to avert overload scenarios. Then, we'll uncover the art of retransmissions, where lost packets are seamlessly recovered, ensuring data integrity. Lastly, we'll delve into UDP use cases, revealing scenarios where speed takes precedence over flawless delivery. By the end, you'll master crafting reliable services and selecting the ideal protocol for your application's unique demands. Let's embark on this enlightening journey together. What sets TCP and UDP apart at their core? TCP, or Transmission Control Protocol, prioritizes reliability through a dedicated connection, ensuring packets arrive in order and data integrity is verified. This method, while slower due to added steps, guarantees a secure transfer. On the flip side, UDP, or User Datagram Protocol, takes a different approach. It's connectionless, sending data without establishing a link, with no promise of delivery. Operating with minimal overhead and speed in mind, UDP sacrifices error checking for lower latency. TCP for reliability, UDP for speed. Choose wisely based on your needs. Imagine trying to have a conversation without introducing yourself first. That's where the TCP three-way handshake comes in. It's like a polite way for devices to say, "Hello, let's talk." The process starts with the SYN, where the client sends a synchronization request to the server with its initial sequence number. The server responds with a SYN-ACK, acknowledging and sending its sequence number. Finally, the client sends an ACK to confirm receipt, and just like that, the connection is established. It's a quick and essential dance of communication before the real conversation begins. And with that, the TCP three-way handshake sets the stage for data transmission, ensuring a secure and reliable connection between devices. In the blink of an eye, a crucial dance unfolds between client and server, the handshake sequence diagram. SYN from the client, met with SYN-ACK from the server, culminating in the final step of ACK. These milliseconds are the bedrock of a reliable connection, each step marked by sequence numbers for seamless data tracking. This intricate exchange sets the stage for communication to flow. Without it, chaos reigns. Ever wondered how a TCP connection says its goodbyes? Well, closing a TCP connection involves a dance known as the four-way goodbye. First, the client politely signals its intention to finish by sending a FIN flag. The server acknowledges this, but may still have a few things to say. Once it's ready, the server then sends its own FIN. Finally, the client wraps up the conversation with a final acknowledgement, officially closing the connection. In this intricate exchange, both sides must agree independently to part ways. It's a delicate process of closure in the digital realm. Ever wonder why congestion control is crucial in networks? Just like highways, networks have limited capacity. If flooded with too much data, packets are dropped, and performance suffers. TCP steps in by detecting congestion and adjusting transmission rates to avoid collapse. This self-regulating feature is the backbone of the reliable internet we rely on daily. Without it, bandwidth-hungry applications would hog resources, causing chaos with packet loss and constant data retransmissions. In essence, congestion control is the unsung hero that keeps our digital world running smoothly. Ever wonder how TCP manages congestion? It's a fascinating process with distinct phases. In slow start, it cautiously begins with a small window, doubling at each round trip until a threshold is reached. Moving into congestion avoidance, the window size increases more gradually to explore available bandwidth without overwhelming the network. When duplicate acknowledgements signal trouble, fast retransmit kicks in, promptly resending suspected lost packets. Finally, during fast recovery, the congestion window is reduced after retransmission, but not as drastically as during a timeout, before resuming congestion avoidance. TCP's congestion control is a carefully orchestrated dance of caution and exploration, ensuring efficient data transmission. Remember, in TCP congestion control, slow and steady wins the race. Ever wonder how your computer efficiently manages data flow during online activities? The congestion window holds the key. It controls the number of packets traveling but awaiting acknowledgement, optimizing data transmission. Picture the rapid exponential growth during slow start, transitioning to steady linear growth in congestion avoidance once the threshold is reached around RTT5. This evolution ensures smooth data flow without overwhelming the network. Remember, understanding congestion window dynamics is essential for enhancing network efficiency and user experience. Ever wonder how TCP ensures data reaches its destination intact? It's all about sequence numbers and acknowledgements. When a packet goes missing, TCP doesn't fret, it takes action. If an ACK goes missing, TCP resends the packet. 3 duplicate ACKs? That's a signal for fast retransmission. And with adaptive timeouts based on network conditions, TCP stays sharp. In a world of uncertainties, TCP's methodical approach keeps data flowing smoothly. Have you ever wondered how TCP decides when to retransmit data? It's all about the retransmission timeout, or RTO. By measuring round-trip time, RTT, and factoring in packet acknowledgement delays, TCP dynamically calculates the optimal retransmission timing. Using a weighted average to smooth out fluctuations and incorporating RTT variance for network unpredictability, the RTO is set to ensure efficient retransmissions. This adaptive strategy prevents unnecessary retransmissions on slow networks and swiftly detects packet loss on fast networks. In essence, TCP's RTO algorithm strikes a balance between caution and responsiveness in data transmission. UDP, where speed triumphs over reliability. In the world of live streaming, dropped frames are favored over delays. Online gaming thrives on quick responsiveness, not perfect accuracy. VoIP calls value minor glitches over lag. DNS queries opt for retrying over TCP overhead. Different needs, same protocol, UDP shines in speed-critical applications. Embrace the trade-offs for real-time success. Ever wondered how a communication protocol can be both powerful and minimalist? Enter UDP, the unsung hero of networking. Its header structure is a mere 8 bytes, containing essential elements like source and destination ports, length, and checksum. In contrast, TCP's bulky headers with sequence numbers and control flags can span up to 60 bytes. This simplicity translates to less processing overhead, reduced latency, and more bandwidth for actual data. Applications can layer their own reliability features atop UDP when needed. Efficiency meets effectiveness in UDP, proving that sometimes less truly is more in the world of networking. Ever wonder how the technology behind web browsing ensures every pixel and line of code arrives flawlessly? From HTML to JavaScript, HTTPS via TCP makes it happen. And what about your emails? TCP guarantees each message is delivered intact, no missing paragraphs allowed. When you download files, even a single corrupted byte can break the entire file. That's why file transfer over TCP is crucial for accuracy. On the flip side, for real-time streaming like YouTube Live, UDP allows for some lost frames to maintain seamless delivery. In the gaming world of Fortnite, UDP ensures player position updates arrive swiftly, making old data irrelevant in fast-paced action. And in network monitoring, protocols like SNMP and Syslog use UDP for frequent updates, where missing one isn't critical. TCP for precision, UDP for speed, the backbone of our connected world. Are you faced with the decision of whether to use TCP or UDP in your application's design? If low latency is critical and data needs to arrive quickly, opt for UDP. This protocol is ideal for applications like VoIP and gaming that are loss-tolerant and require swift data transmission. On the other hand, if perfect delivery is paramount and data integrity is crucial, TCP is the way to go. It ensures reliable and ordered delivery, making it suitable for tasks such as file transfers. When determining which protocol to utilize, consider your data requirements, timing constraints, and tolerance for loss. Make an informed choice based on these key considerations to optimize the performance of your application. Ever wondered how TCP and UDP stack up against each other in the digital realm? TCP, the reliable workhorse, requires a handshake for a connection, ensuring guaranteed delivery and orderly data arrival. On the other hand, UDP operates connectionless with no setup, offering speed and minimal overhead but no reliability guarantees. While TCP boasts extensive error checking and congestion control, UDP keeps it simple with basic checksums and shifts the congestion responsibility to applications. Each has its domain. TCP suits web and email, ensuring data integrity, while UDP shines in streaming or gaming, prioritizing speed over reliability. Choose wisely based on your needs, the thorough reliability of TCP or the swift efficiency of UDP. Ever wondered how to combine the speed of UDP with selective reliability? Enter custom protocols atop UDP, like the revolutionary QUIC protocol. Powering HTTP/3, it marries UDP's velocity with TCP-like dependability. WebRTC takes it a step further, offering real-time communication with selective retransmission for crucial packets. And in the realm of gaming engines, custom protocols ensure only vital state updates get resent, boosting efficiency. This tailored approach gives developers precise control over data reliability, fine-tuning performance to suit each unique scenario. In a world where speed and reliability intertwine, customization reigns supreme. Is TCP always the best choice? In reality, its reliability can lead to delays that are worse than occasional data loss for real-time applications. When it comes to UDP, is it really as unreliable as people think? Actually, UDP can be perfectly reliable on good networks, offering a lightweight protocol that allows applications to implement just the right level of reliability. And what about congestion control? Does it only benefit others? The truth is, being a good citizen with congestion control benefits your own connection too, as overwhelming the network can lead to packet loss and retransmissions. Remember, choose the right tool for the job and consider the nuances of each protocol. Ever wondered how data travels reliably across the vast expanse of the internet? It's all thanks to TCP, the protocol that ensures your messages reach their destination intact. Through meticulous handshakes, acknowledgements, and clever retransmissions, TCP guarantees the safe passage of your information. Meanwhile, UDP opts for speed over certainty, making it ideal for real-time applications like gaming and streaming. So, next time you're choosing a protocol, remember to consider your application's specific needs. Whether it's the precision of TCP or the swiftness of UDP, there's a perfect fit for every network challenge. As we wrap up, let's dive into the practical side of things. Get your hands dirty with Wireshark to capture and dissect TCP handshakes live. Then, craft a basic UDP chat program for a taste of connectionless communication. Dive into coding with basic congestion control logic to unravel the algorithms at play. Compare TCP and UDP performance across different file sizes and network conditions for insights. Delve deeper with RFC 793 for TCP specifics, and RFC 768 for UDP details. Look ahead to the future with the QUIC protocol. Discover how streaming giants like Netflix and Spotify choose protocols. Mastering transport protocols equips you to craft top-notch networked applications and troubleshoot issues effectively in your career.